All right, so now let's spend a few minutes looking at how some seismic attributes can help us better understand some cases in shallow marine and shelf environments. Okay, so of course, I'm going to say let's start with our analogs. So here's an analog of a tidal channel. This first one is Mont Saint-Michel in Normandy, which has some of the highest tides in the world. And then the second one is from the Coos Bay in Oregon. And so one of the interesting things to notice is that that it looks dendritic kind of as you move towards land, which isn't always something that we would think about right offhand. But you can notice that here in the Oregon area, and then also in Mont Saint-Michel. That dendritic pattern kind of points towards land or away from the basin. So those are things to kind of keep in mind as you're analyzing your seismic. Okay, so looking at some tidal channels and seismic now, we're in British Columbia, in Canada, and what we've got here are a couple of horizon slices that go through our seismic data volume here, and then a coherence time slice. And when we look at our seismic and vertical section, we can see that there is information there. We can see some variation in the patterns. It's discontinuous, it's high amplitude, but it's hard to get an overall sense of what exactly is going on. So it's not quite as complete an image or complete as an image as coherence and what we would like to have in order to interpret it. So now we can move through the horizon slices, kind of moving down in time. So from our 0 milliseconds where we've looked at, picked the seismic data, we can move down in time from -4 milliseconds to -8 or up in time also. So we're doing those kind of phantom horizon slices, just moving up and down so that we get a better idea of the channel system. And we're doing this in our coherence volume. And so you can see as we move from lower and then we move up higher, we can see the development of some of the systems and the disappearance of the not the full disappearance, but we see the disappearance of the tidal system as we move higher out of that area. And you can pick out some of the dendritic features, which can give you more information about that tidal system as a whole. Here's an example using a different set of seismic attributes. So doing red, green, blue, color blending of horizon slices. So we're doing a visualization technique from the middle Miocene, blending those spectral elements together so that we can see the lineations from the paleo shoreline. So we've got kind of these long shore accretions. You can kind of see them in this area here with the wave direction, and that helps us understand the paleo wave direction. So other things that we can pick out in the seismic data using some seismic attributes. This is another case. Now we're in the Gulf of Mexico, and we're looking at some erosional scarps, or we're noticing an erosional scarp that we can see both in the time section, so kind of marked by this pink arrow. You can see that erosional scarp in the vertical sections. And then you could also see it in the time section, but it's very, very clear when you image it using coherence, the coherence volume, here just with a time slice. And then it also shows up if you look at this east-west energy-weighted coherent amplitude gradient volume. So a slightly different technique that picks up the erosional scarp for you. All right, let's look at a couple examples of sediment waves, which are other features that we often see in these systems. So here's a case of sediment waves from offshore Morocco. We're just looking at the seismic amplitude data in this case. We've got, kind of our seismic area here. There's some salt in the area. We've got some base Albion sediment waves showing up right in this area. And then also Middle Jurassic age sediment waves. And you'll notice that in this vertical slice of the seismic amplitude data, they're not really jumping out at you. And so this is where looking at the information slightly differently can help out. And so in this case, we're looking at the seismic amplitude map. We're 32 milliseconds above the top of the Albion. And so we can really see just in the change in amplitude, these sediment packages. And so you could see areas of wave bifurcation. You can see that the crests are actually axially oriented southwest, northeast, kind of oblique to the paleo shelf. And so a lot of information is available if you look at the seismic data the right way. That just seemed very subtle when we looked at it in that last slide of the vertical section. Here's another image of the sediment waves in offshore Morocco. Again, still just looking at the seismic amplitude map. So now we're 28 milliseconds below the top Albion, and those sediment waves show up really, really clearly just by using a amplitude attribute. All right, let's look at a case with some evolution of progradation. And so this is a really neat example showing the evolution of the canyons, of tidal channels, of progradational filling of canyons, of shallow gas channels, all in the Taranaki Basin, offshore New Zealand, just to the west of the North Island. And so in this case, we're using spectral components. So at 35, 45, and 55 hertz, we've done a red, green, blue, co-rendering of them. And then one of Kurt Murford's students made an animation of it, kind of moving through the system. And so you can notice as we go deeper, or no, we're coming shallower, the evolution of these channel systems. And so here we go again, just starting at the top and then moving deeper. And you can see some of the channels. You can see some of the tidal features that are coming out in this spectral coherence volume. You can see some of the channels. So a lot of information is being shown. And I do want to mention that being able to show movies like this, so it replicates what we would do as seismic interpreters scrolling up and down or side to side or along an arbitrary line. And it can really help show the rest of your team, like look at these channels down here, tidal channels down there. They can really help show the rest of your team what you're seeing in the seismic data, and doing it interactively like that is a really valuable tool. There's a few more images that were made related to this. In this case, we're using the reflector convergence attribute co-rendered with seismic amplitude. And so this is kind of being shown on a vertical section and then also on a time slice with a co-rendering. And what you're able to see are some of the conformable reflectors in this case. And then as we move through, you can see here some of these cliniforms. I'm trying to point them out with my pointer right here, but we're using that reflector convergence because, as we know, you get the cliniforms and the progradational features, and so you end up with a kind of divergence and convergence of those reflectors. And so we can see those really clearly showing up. We can also see the canyons being highlighted that are formed in this system. And as we move down now with the time slice, some of the turbidites related to the system appear. And in this case, we've kind of got the core of the volcanic feature. And so just to wrap up with these few kind of couple of examples I wanted to show you, some of the things you want to keep in mind, again, with shelf and shallow water features, are that the geometric attributes are really, really crucial. So coherence is one of the attributes I run for almost everything. It really helps visualize the 3D data volumes and see the geomorphology. Other things that you may want to pay attention to or try out on your data are the seismic, the spectral decomposition techniques, the co-rendering of red, green, blue, and even trying out reflector convergence if you're looking for a seismic geomorphological pattern where you would expect that converging of your horizons. As always, thanks for listening.